I will begin with recalling the main principles of the JPEG standard for image compression. This algorithm is based on dividing an image into 8 on 8 pixel blocks. Each box is converted into a vector of 64 coefficients. Conversion consists in computing two-dimensional discrete cosine transform of the pixel blocks. Then the resulting matrix is quantized, and then we take quantized matrix elements in the zigzag order. The aim of the conversion is to obtain a coefficient vector well suited to entropy coding. This well suiting is in this that there are only few non-zero coefficients, and these non-zero coefficients are separated by long runs of zero valued coefficients. And the standards provides Huffman entropy codes optimized to coefficient vectors of natural continuous tone images. In my research, it's important that we differentiate between DC and AC coefficients of the discrete Fourier transform. DC coefficients, direct current coefficients. This name is caused because the algorithm was invented by some people related to electrical engineering. This DC coefficients are related to the average intensity of 8 on 8 pixel blocks, and values of these coefficients are similar for adjacent blocks. On the opposite, AC coefficients are related to variations of pixel intensity. They represent variations in various frequencies and various directions. Lower frequency AC coefficients are more frequently non-zero after quantization, while higher frequency coefficients are more frequently are zero values and valued and occur in run of zero coefficients. Both AC and DC coefficients are entropy coded using Huffman codewords and value bits. Codewords occur in series related to pixel blocks. Each series describes DCT coefficients of a subsequent box of 8 on 8 pixels. Coefficients are described indirectly. Namely, first pair of code works described not simply DC coefficients, but the difference between DC coefficients of the current block and the DC coefficients of the previous block. Then each of subsequent pairs of code words describes a value of one non-zero AC coefficients and the number of zero-valued AC coefficients that precede the non-zero one. There are some special code words, but I neglect this in order to keep clarity of our discussion. The last thing to recall is how DC coefficients are coded using category value codes. Namely, values of coefficients are coded indirectly by using one Huffman code words that describes value category, and then this code word is followed by bits that determine a particular value of this category. This is example, for example, 00 in this table. For example, 00 Huffman codewords describes only one element category, namely zero value, but 010 code word describes the category which consists of plus one or minus one value. And this code word is described by one value bit, which selects either plus one, either minus one. And then the third category consists of four values, minus 3, minus 2, 2, 3, and this code word is 0, 1, 1, and is followed by 2 bits which allow to select one of these four values. The compression effect is achieved by assigning shorter words and fewer value bits to categories that occur more frequently. And now we have a background to switch to the general subject of my work. Namely, my work is related to format compliant encryption of JPEG files. Such algorithms combine encryption with data coding. They preserve bitstream structure even though image contents can be hidden. In the case of encryption unaware decoder, in case of not knowing crypto key, user obtains unreadable images or at least unreadable fragments of image like human faces displayed on screen. But regardless of whether image is encrypted or no, always there is access to metadata, image description, thumbnail, resolution, which can be used for indexing and retrieval purposes. So these algorithms allow for designing applications in which user can browse among thumbnail images and only at the last stage of displaying image it is asked for providing password to show high quality image. Such algorithms are less efficient and less secure than general purpose ciphers, but as I said, found some practical applications. It is possible to consider two categories of approaches to format compliant encryption. Simpler solution consists in simply shuffling pixels before normal encoding. Shuffling is determined by crypto key. It can consist in rearranging 8 on 8 pixel blocks or single pixels or pixels in blocks. Block of pixel can be rotated so as to produce an unreadable image, and then this unreadable image is compressed using normal JPEG encoding. However, in this solution, unreadability of images comes at the cost of reducing spatial correlation among pixels. So the correlating transforms like DCT, discrete cosine transform, wavelet transforms work less effectively. In a short word, such approaches produce larger output files compared encrypted output files are larger than files obtained without encryption. More advanced solution consists in more wise shuffling of transform coefficients or entropy codewords. Such solutions has little effect on bitrate or even no effect, or they preserve file size. Encryption doesn't causes increasing file size. Everything comes at some price. Such solutions are less secure. Encryption can be bypassed so as to reveal contours of images. This is example of the Lena image. This is in middle. We have results of normal decoding of JPEG file encrypted by shuffling only AC coefficients of DCT. And on the right hand side, we see results of decoding encrypted stream bitstream with neglecting DC coefficients. Simply DC coefficients are zero. As we can see, image is not perfectly readable. Nevertheless, we can see edges, we can see contours, so some information can be revealed even though we don't know encryption key. My solution, my algorithm somewhat improves in this respect. This is on the left hand side. We can see the same decoded image, somewhat large. This is a result from one previously known solution proposed by our Unterweger and colleagues, while on the right hand side we can see image decoded from encrypted stream produced by my solution. As we can see, my approach allows for somewhat better hide controls, edges, even though encryption can be still bypassed. Information is somewhat better secured. My solution, as to its general principle, is a polygram substitution cipher. In general, such ciphers consist in replacing several symbols of a text with the same number of other letters. In my case, symbols, letters to be replaced are Huffman code words that describe DC T coefficients, only the main DCT coefficient and the first non-zero AC coefficient. Code words are replaced, which results in changing their lengths, so accompanying value bits must be moved so as to adjust to replace the coefficients. In order to preserve the bitrate or file size, in my approach, only substitutions are allowed that preserve sum of lengths of these two Huffman code words, and that preserve the sum of numbers of value bits. In this slide, we can see a table which shows sum of many possible combination of DC and AC related Huffman code words and value bits. These are two all possible 12-bit combinations. This combination has been grouped with respect to the total number of bits and number of value bits. So we can see one group is there are combinations which consist of two 11 bits related to Huffman code web and 1 bit related to value bits. The second category consists of combination in which 10 bits are related to Huffman code words and 2 bits are related to value bits. And so on. In my approach, we replace Huffman code words inside one such category. So we can keep constant the number of value bits. This is a diagram which shows the encryption and decryption processes of my solution. In a short word, original Huffman code words produced from normal JPEG encoding. These code words are used to determine the substitute group. Then substitute code words inside a group are determined by an index obtained from pseudo-random number generator. And this generator is initialized by a cryptographic key. And this process can be simply reversed on the decoder side. Without a proper cryptographic key, we don't know how code words have been substituted. Such substitution is constrained by some limitations. For most images and for most JPEG quality settings, code words can be substituted sufficiently often so that it's impossible to recover a readable quality image without knowing the cryptographic key. However, when an image is encoded with raw quality settings, some pixel blocks or equivalently code word combination might occur to which the proposed cipher cannot be applied. The default Huffman dictionaries code tables determine not so many such pair of code words that have no substitutes in accordance to my approach, but in many natural images, only a small subsets of replaceable combination of bits occur in the related bit streams. This can be explained by the following table. This table shows combinations, 12 combination of code words and value bits related to DC and AC coefficients. For each of these combination has no substitutes in accordance with my algorithm. This seems to be not a problem because in total there are about 2000 DC-AC pairs of code words related to the default Huffman code table. But the problem is that such combination can occur quite often in for low quality settings. In general, taking in this plot, we can see distribution, or maybe it's better to say visual representation of number of pairs of particular group of substitutable code words, and each substitutive groups is has two properties, two parameters: length of Huffman code words and number of value bits. And the color represents how many substitutes occur in a group related to particular combination of length of Huffman code words and number of value bits. This plot seems to be dense. Many combination have two or more substitutes, but for real images situation if worse. These are corresponding plots which show how distribution of combination of code words depends of JPEG quality settings. We have quality settings 25%, 50%, and so on. And we see then even for very accurate compression, we have much denser distribution, sparser distribution compared to the distribution defined by only Huffman dictionary. This limits possibilities of encryption by code words substitution. The situation is more worse when there is less overlap with such a plot, with this plot defined by pure code tables. And the general effect that decreasing quality increases the number of pixel blocks for which are described by only DC related bits, so that there are no bits related to non-DC, non-zero AC coefficients, and to such pixel blocks our cipher cannot be applied. Fortunately, situation is not very bad. For reasonable quality settings, it means even for only 25%, our cipher is able to modify considerable areas of an image. This table show how many 8 of 8 pixel blocks can be replaced in accordance with our cipher. As we can see, This is from about 50% to more than 80%. So this is sufficient to rather well hide encrypt image contents. Related parameter of encryption efficacy is the average number of substitutes per block. This average number varies from 1.3, 1.8 to even 3 for quality settings, change from 25 to 100%. So to conclude my work, my cipher is slightly but evidently improved compared to the previous works. The advantage of my solution is that it can be implemented as simple post-processing of JPEG bit streams, so it can be built up on existing codecs. On contrary, some previously known solutions require modifying codec internals or they require buffering entire image. So my approach is more lightweight. Some innovative aspects of my works are these tables and these plots, which reveal some new statistical information about distribution of DCT coefficients and Huffman codewords occurring in JPEG bitstream related to natural images. That's all. Thank you for your interest in my work.
Thank you very much. Do we have questions to the presenter? I don't see questions. I have a question about the plans with respect to this work. Do you plan to further enhance the method, or is it finished work at this point?
From the point of view of researcher, this work is rather complete because I developed an algorithm, characterize its main properties. The next step would be to implement this algorithm in more commercial way, especially my present implementation neglects some special code words which occur in real JPEG files. It's not difficult to handle these special elements of bitstream structure, but this is more engineering than research work because I mean byte stuffing to avoid occurring some an inappropriate combination of bits in which are necessary to synchronize the decoder with bitstream. So I think in case of some interest from industry, I will develop this solution. In case of no interest, I think I will switch to modern thinking about new algorithms.
Okay, thank you very much for a very interesting presentation.